As we continue our work in section 2.5 on transformations, I'd like to give some general information and overview on our methodology. I referenced this in the lesson 2 file that I posted on Blackboard, and this transformation handout is also posted on Blackboard. The PowerPoint presentation you would have just watched gives a nice visual illustration of how transformations work, but I want to speak a little bit more to the algebraic and tabular method that we're going to use in our course. For starters, we're just going to focus on vertical and horizontal shifts. Now, in general, when you look at transformations, there are really vertical manipulations and horizontal manipulations. Vertical manipulations, we will be changing the y-coordinates. Horizontal manipulations, we'll be changing the x-coordinates. Now, in general, you can identify a vertical transformation because it is some manipulation or argument outside the function. So for a vertical shift, we can shift the graph up by c units or shift it down by subtracting c units. Notice how the plus c or minus c is outside the argument of the function f of x. And there you see this is the algebraic manipulation we'll make to our table of coordinates. We can add c units or subtract c units from the y coordinates. Now horizontal shifts, or horizontal transformation, you will see that plus or minus c or manipulation inside the argument of the function. Now, one thing you want to note, with horizontal shifts, a plus c manipulation really means a shift left in the negative x direction, which is opposite of the sign you see. So that manipulation, we will subtract c units from the x coordinates. And then if you have x minus c as a horizontal shift, well, that's really a shift right of the graph in the positive x direction. So we will add c units to the x coordinates. So most people find it easier to understand vertical shifts, right? Plus c goes up in the positive y direction, minus c goes in the negative y direction or down. If you can understand vertical, just remember that horizontal shifts will be opposite. That plus really goes in the negative x direction, minus goes in the positive x direction. So this is the methodology that I've referenced that we're going to be using when we apply transformations in this section. So we'll come up with a table of coordinates where we will identify a minimum of 5 coordinate points of the base function f of x. Then we're going to identify the transformations in the given function in the sequence in which they must be applied. Now we're going to start more simply with singular transformations. However, you could think of transformation problems as somewhat like a recipe. You have to identify what ingredients you have and in what order you process them, so to speak. So at the beginning of each problem, I'm going to identify the transformations, and there will be a certain sequence that they must be done in. We will get to that later in part 2 of chapter 2.5. And then we'll use the manipulations you saw in that transformation handout to algebraically manipulate the table of coordinates, starting with the base function f of x, going through the various transformations, and then eventually getting a final table of coordinates where we can graph the final transformed function. Let me show you an example of a vertical shift and how we will approach working these problems. So this is on page 284 of your textbook, and you'll see there's a nice visualization of the vertical shift, right? F of x plus c, it shifts up. F of x minus c, it'll shift down. So let me show you example 1 here. And it's a vertical shift downward. Use the graph of f of x equals absolute value of x to obtain the graph of g of x equals absolute value of x minus 4. So when we look at this example, this is our base function f of x, the absolute value function, and then this is the transform function. And so the methodology we're going to follow is, well, what transformations do we have? What order do we do them in? And what do we have to do with that transformation? So that's a key first step. And with vertical shifts, you'll always see some manipulation outside the function. So notice we have, this is the base function, but this minus 4 is a vertical shift down and it's outside the argument of the function. That's how I know it's a vertical shift. But what I always want to do is identify the transformations I see. So I'm going to identify that there is a vertical shift down by 4 units. And what's my manipulation? Well, because it's a vertical shift and it's negative, I'm going to subtract 4 from the y coordinates. So this setup is very important with transformation problems, particularly when we get to the more complicated ones where there are multiple transformations that have to be done in a very specific sequence. So again, this is really the recipe analogy I'm trying to emphasize, right? What do we have? What order do we have to do it in? So now that we've set up the problem, I'm going to start out with my base function table of coordinates. And because it's the absolute value function, right, we can use those x values minus 2 to 2. And of course, the absolute value of the negatives will just be the positive. So notice, I haven't even really memorized, okay, the absolute value function. I'm just taking the absolute value of this column of numbers that you see here, the x values. And then I'm just going to apply our first transformation. So again, my table of coordinates, I'll have x, and then I will have g of x. All right. Now, because this is a vertical shift, we're manipulating the y coordinates, but notice we're not changing anything with the x coordinates. So this column here of x values, we're not going to change at all. There'll be no manipulation. So I can just copy that column of numbers over. And now what I need to do is just take these y values that you see under f of x and just subtract 4. So 2 minus 4 will be minus 2, right? 1 minus 4, minus 3. 0 minus 4, minus 4, right? 1 minus 4, minus 3. And 2 minus 4, minus 2. And so these are really the final coordinates of the transform function that then we will graph. Now, to save a little time and show you a little nicer graph than what I would draw by hand, I'm just going to utilize the pictures you see in the textbook. But if you look at these 3 points here, we always use 5, but you might recognize there's that minus 4, 0 point, 4, 0, and 0, minus 4. Those are the points that we calculated algebraically. The text shows this problem being solved graphically by just moving the graph around. But that's not how we're going to solve these problems. We can do everything algebraically using tables of coordinates and then graph the final function. So even though a couple of the points the textbook uses are different than ours, if you look carefully, here's our point 0, minus 4, which you see in the graph, and here's the point 1, minus 3, minus 1, minus 3, and here's minus 2, and 2, minus 2 in the graph, which matches our table of coordinates. Now let's look at a horizontal shift example. Again, the text nicely illustrates the horizontal shift concept. Notice the plus or minus c is now inside the argument of the function, but remember, it's now opposite what we see with a vertical shift. With a vertical shift, plus c means we add c to the y coordinates, minus c means we subtract c from the y coordinates. Remember, with horizontal, it's opposite. Plus c really means we're shifting to the left. We subtract c units from the x coordinates now, and minus c is really a shift to the right. So we're going to add c units to the x coordinates. So let's take a look at example 2. And now use the graph of f of x equals square root of x to obtain the graph of g of x equals square root of x plus 5. So as we look at example 2, remember with the transformation problems, always start to set up the problem correctly initially. Identify what transformations do you have, what order you're going to do them in. So here's our base function, the square root function, square root of x, and here's g of x. And where you really want to look is right here. Notice there's the plus 5, okay? Now remember, this is a horizontal shift because notice how it's inside the argument of the function. You'll see it's underneath the radical. It's not outside the radical. If it were, it'd be a vertical shift, but it's underneath the radical, which means it's a horizontal shift. So we have only one transformation. Again, identify your transformation. This is really going to be a horizontal shift left, right? Plus really means going to the left by 5 units. And so what's our manipulation? Well, now I need to subtract 5 from the x coordinates, right? Remember, a horizontal transformation, we need to change the x coordinates. So again, there's our recipe. There's sort of our plan for the problem, what we have to do. So now let's create the table of coordinates for the base function and solve. So the square root function is one of those exceptions where we can't have those values of -2 and -1 like most of our functions, right? So start 0, 1, 4, 9, and 16. And then this is the square root function. I'm just going to take the square root of these numbers. So square root of 0 is 0. This will be 1, 2, 3, and 4. And now again, let's come up with our next table of coordinates. This will be x and g of x. Now, like I said, in example one, we were manipulating the y coordinates and not the x, so we just copied the x values. But now we're going to have to manipulate the x coordinates, but we're not changing the y coordinates. So again, I can copy this whole column of numbers down because I'm not going to change them. Now, what's our manipulation? Well, I need to subtract 5 from all these coordinates. So 0 minus 5, right? That'll be -5. 1 minus 5, -4. 4 minus 5, -1. 9 minus 5 would be 4. And 16 minus 5 would be 11. Right? So there's the algebraic manipulation. And now we have our table of coordinates. So when I go back to the text, you'll see the graphs. And again, the text is emphasizing a graphical method. Again, we're going to utilize a tabular method. But here's the square root function, and they only show 3 of the 5 points that I have, but that's okay. But you can visually see that everything's moved off to the right, to the left, 5 units. So if you focus on these points, right here, this point 0, 0 is now at -5, 0. This one's -4, 1, and that one is -1, 2. And so if you look at the table of coordinates that we created here, notice these first 3 points, right, -5, 0, -4, 1, and -1, 2, those are exactly the same points you see in the graph. Again, we don't have to do any intermediate graphing. We can calculate the final points all algebraically using manipulations of the table of coordinates, and then just plot the final function. So as extra practice, particularly because I emphasize this method, I would like everyone to work on checkpoint 1 and checkpoint 2 as extra practice. All right, so these instructions will be on our Blackboard site, and the checkpoints are always right after the examples in the text. So you can find example 1, checkpoint in the e-text, checkpoint 1 will be right after that, and in example 2, right after example 2, you'll find checkpoint 2. All right, so you can utilize this file, which I will post as a guide, but this is really how you want to practice these problems. This is how I'm going to solve them.